All right, so we're going to go ahead and do an example of calculating the pH of a weak base titrated with a strong acid. So the thing to remember is that we're starting with our weak base and we're adding strong acid to it. And we need to work out if we are before, at, or after the equivalence point before we know how we're actually going to deal with this issue. So the first thing we should do is work out the number of moles of weak base that we have and the number of moles of our acid that we've added to it. So for my weak base, which is in this case ammonia, um, so my ammonia, I'm going to take my concentration, which is of course in moles per liter. So I'm going to actually write that out as moles per liter, 0.1300 moles of ammonia for every 1 liter of ammonia. And we know what volume we have. We have 52 milliliters. So we're going to have to do a unit conversion there between milliliters and liters. So we can just stuff that on the end there, that's fine. Um, So 1 milliliter is 10 to the minus 3 liters. So I can put my 1 milliliter on the bottom there and 10 to the minus 3 liters up on top. So we can see that our milliliters and our liters will cancel out, giving us our number of moles of ammonia that we initially have. So that comes out to be 0.00. How many zeros? 6760 moles of ammonia. Okay, so let's see if I can make that a little bit tidier. All right, so that's how many moles of ammonia that we have, and then I need to do the same for the number of moles of acid that we have added. So the key to this is if we have added less moles of acid than the number of moles of base that we have present, then we've only neutralized a portion of that, okay? Um, if we've added exactly the same number of moles of acid as number of moles of base that we have there, then we've completely neutralized it. So because this is a weak base, we're then going to be basically looking at the conjugate acid reacting with water, the hydrolysis of the conjugate acid. So that would mean we'd need to do an ice table to work out the pH. If we've gone past the equivalence point, then that means all we have at this point is excess acid. So we're just going to work out how many moles of excess acid we have. And because it's a strong acid, it's going to be very straightforward to work out our pH. So let me look at our acid then. My HClO3, my perchloric acid. My concentration was 0.8900 moles per liter. So I'm going to use that to calculate in, let's see, what was it, 3.9 milliliters, uh, how many moles of my perchloric acid I actually have. So was it 3.9 milliliters? And then convert milliliters to liters, like so, with a little conversion factor. And that gives me 0.003471 moles of my perchloric acid. So I have less moles of acid that I've just added than number of moles of base present. So that means I am before the equivalence point. I have not yet neutralized all my ammonia, my weak base. So what I need to do, the easiest way to do this is what we have is going to be a buffer solution because the product of that neutralization reaction is going to be that we're generating some of the conjugate base, right? Because if I have, well, any acid, it doesn't really matter. If it's a strong acid um, in aqueous solution, that is going to completely dissociate. So we'll have the perchlorate anion, that doesn't do anything, and the hydronium ion, and that is what is going to be neutralizing our ammonia. So for any weak base, doesn't matter what it is, base is a proton acceptor, acid is a proton donor, so that reaction then is going to look a little bit like this, NH4 plus, it's conjugate acid of the ammonia. And water. So that's our neutralization right there. So for the combination of a weak base with a strong acid, that product is going to be the conjugate acid of the weak base, which in and of itself is going to be weak acid. So that's why we have to deal with this a little bit differently. So we can use the Henderson-Hasselbalch equation because this is essentially a buffering solution, okay? But we do have to do that stoichiometry problem because the number of moles of our weak base, ammonia, have been reduced by that neutralization. The number of moles of our ammonium, its conjugate acid, have increased from 0 to whatever they are. So we're going to do a little stoichiometry calculation. So we are before the equivalence point. So that is our buffer region. And we're going to use the Henderson-Hasselbalch equation. You can do a full-on ice table, just like we did before we learned the Henderson-Hasselbalch equation. You can solve this as an ice table. It just takes longer, and we ain't got time for that. So stoichiometry then. I've got my ammonia, and I've got my ammonium, which is the conjugate base of ammonia. Sorry, conjugate acid of ammonia. So I've already calculated my initial moles. My initial moles of ammonia was that 0.006760. Let's just sort out the spacing a little bit. And initially I have no ammonium. And then I'm going to add my acid. So adding the acid is going to neutralize. Well, how many moles of acid did I add? 0.003471 moles of acid. So that's going to take down the number of moles of ammonia by the same amount, and it's going to generate the same amount of moles of my ammonium, so plus 0.003471. So if I do the math, I now have my new moles. So after that addition, I should have that's going to be 0.003289 moles of ammonia and 0.003471 moles of ammonium. So this is what I'm going to be able to put in my Henderson-Hasselbalch equation, which, if you remember rightly, pH equals pKa plus the log of the concentration of base over concentration of acid, or it can be moles of base over moles of acid because it's a ratio, right? So in this case, I'm just going to do moles of base over moles of acid. So moles of ammonia over moles of ammonium. The only thing is I don't have pKa for ammonium, okay? I've been given pKb of ammonia, so that's good. That means I'm almost there, okay? Because we can use the fact that pKa plus pKb for a conjugate acid-base pair equals pKw, which is the P of the ionic product of water. So 1 times 10 to the minus 14, do minus log of that, you get exactly 14. So now I can calculate my pKa for ammonium, whoopsie, wrong pKa for ammonium NH4 plus is going to be 14 minus pKb for ammonia, which is 4.74. That comes out to be 9.26. Okay, so now I'm ready to just use my Henderson-Hasselbalch equation with the number of moles of ammonia and ammonium I have. So my pKa is 9.26 plus the log of the number of moles of base, which is my ammonia, so 0.003289, divided by the number of moles of acid, which is my ammonium, 0.003471. Obviously, you may need to use brackets, etc., to make your calculator be happy with that. I would normally at least do this. Sorry for ugly brackets. Okay. And that comes out to be, should still be a basic pH, right? Because we haven't neutralized all that base. Comes out to be a pH of 9.23624. 9.24 to 2 decimal places. Okay. So that's what you need to do if you are before the equivalence point.